Hello, my name is Lucas. I am part of the propulsion sector and I'll give you an overview of the process we took to build our solid rocket motor. To start the project, we chose a sugar-based propellant that is made of 65% potassium nitrate and 35% sorbitol. To calculate the operating conditions and internal design of the motor, we use a combination of our own Python codes and softwares such as OpenMotor and BirdSim. To operate in these conditions, we use an aluminum alloy for the casing and bulkhead, and steel in the nozzle. For sealing, we use high stiffness or rings and fixate the bulkhead and nozzle with screws. To validate our design, we use FEM and CFD simulations in addition to hydrostatic and static tests.
Our avionics system was validated both on ground, checking the overall functionality and the ejection logic of the system, and also was validated more than once in our training rocket FTK for checking the behavior of the altimeter in a real operating environment. And for have compliance with the competition's regulamentations, we will have one COTS altimeter that is easy mini to be sure that even if our systems fail, we can safely eject and retrieve our rocket. And we also will have a COTS GPS tracker with telemetry to be sure that if for any reason we are unable to access the rocket after landing, we can safely retrieve flight data and apogee.
For the structural part of Nebula, we have laminated the airframe using fiberglass type E, using the Cosmos wet layup method and a lamination machine created by the team in order to give the rocket more resistance while still being light. The Nebula bulkheads are made of MDF using a CNC machine for their manufacture. Both the bulkheads and the airframe parameters were simulated using the FEMAP software with an Astron solver for static analysis, having its boundary conditions well defined in order to analyze its properties, safety factor, and reassure that we're ready to launch.
In the Nebula's payload, only one sensor is used, a force resistor sensor, responsible to provide a voltage variation by placing a reference weight on top of it, which is measured by a SPA266, then calculated the estimated acceleration of the rocket.
Regarding the Nebula's parachutes, we obtained the main parameters through a software developed by the team. The material we use for the construction of the canopy is nylon 70 resigned, and for suspension lines and the shock cord, we choose polyamide ropes. The parachute is designed to bring the system to a terminal velocity of approximately 7.5 meters per second. The ejection system chosen was the pilot technique. To ensure the integrity of the canopy and the suspension lines, a heat shield that was developed by the team is used. It is composed of 2 layers of nylon 600 fabric, which is interpassed with a layer of fiberglass.
For the aerodynamics of the rocket, we've done flow simulations using the software OpenFoam, so we could take the drag forces around the rocket body. The static margin used was 1.5 calibers to maintain the rocket stable. And for the materials, used PET G with a 3D printer and carbon fiber in the nose cone. And the fins, we used plywood with the CNC and covered it with glass fiber. The fixation of the fins was made by a fins ring where the fins are screwed and it goes inside the rocket.